Okay, so thank you for this kind of broad attendance. And I think, sorry, yes. Sorry, I'm still in the Japanese mode of kind of state of mind. So yeah, thanks for the attention. And also thank you to the organizers, first for the invitation, and secondly for placing me right after Caitlin, because I think it's a very kind of nice and convenient arrangement. So my name is Max. I will talk a little bit about myself later in this talk. So the content of this talk, so in contrast to what Caitlin did, we're focusing on like maybe in detail on one or two projects. I want to kind of show you several things, which is kind of the style that my former supervisor, Professor Tokura, likes. But maybe I will cut something at the end because we can't have enough time. So the main emphasis is on skyrmions and then also on spin dynamics that Caitlin discussed from the theoretical side. I want to show you both some experimental unpublished work on an insulating material and some published experimental work on metallic systems. Okay, so just repeating Caitlin's introduction on scalar spin chirality. So for the purpose of what we are doing, we typically distinguish two cases. Namely, one would be a discrete kind of description where you have some sort of atomic cluster where you define the spin chirality like Caitlin did as a triple product of three nearest neighbor spins. But in the field of skyrmions, people typically like to replace this local spin by some continuous magnetization field because you have a very large spin texture, much larger than the distance between two atoms. So then in this continuum model, you would define an object called the emergent magnetic field, here shown as this BEM, which is essentially very closely related to this triple product. So this is essentially kind of the a product of the continuous field with its slightly translated equivalence. Okay, so before starting on fluctuating spin chirality and transport properties, I want to recap some of the work we did around 2 or 3 years ago, namely developing new materials with skyrmions. When I first came to Japan, I was very interested in studying kind of the synthesis and characterization of new compounds from the experimental side. And at that time, one interesting trend was to realize skyrmions that are only around 2 or 3 nanometers in size, so extremely small. And the idea is that you would have a very large emergent magnetic field because this spin chirality, which is typically quantized on the magnetic unit cell, would be squeezed into a very small area. So we expected very strong transport responses from small skyrmions, and we found skyrmions in a variety of intermetallic compounds, so particularly triangular lattice material, a Kagome type structure, and this is a work by another group at University of Tokyo where they used a tetragonal material. And people who are familiar with heavy fermion physics or quantum criticality, so very fundamental kind of correlation physics, may recognize some of these crystal structures because we simply took the heavy fermion materials and put some kind of spin or like a Heisenberg spin on the magnetic side. So Heisenberg spin would be a spin that can rotate in every direction in space, for example, gadolinium, and can form these twisting spin textures. So a typical phase diagram looks like this. So you have some sort of phase transition, in this case, relatively low temperature, around 20 Kelvin. Then you have a skyrmion lattice at an intermediate region of temperature and field. And this region of field shows both a clear skyrmion pattern in the real space image, which maybe is hard to recognize on this slide, but also very strong transport responses. And so to reiterate, what's new as compared to non-central symmetric materials where, in Germany, of course, there's been so much work, for example, on mangan silicide or some interfaces which break inversion symmetry. So here you have this Dzieradziński-Marie interaction, which creates a spin texture on a relatively long period, for example, 10 nanometers or maybe 100 nanometers. And in these new compounds that we pioneered in Tokyo, you would have no DMI on the free energy level, at least, because they're centrosymmetric materials. So the DMI term is not allowed on the free energy kind of description level. You would instead rely on Ruderman-Kittel-Kasuya interactions, which essentially want to produce a periodic spin texture. And the spin pattern period can be smaller than 5 nanometers. So you can have this very dense spin texture, actually in most recent work down to 1 nanometer. So you can have a spin vortex which has only around 9 or 10 atoms in it. So like it's not really a skyrmion anymore in the traditional description, traditional meaning of the sense, but it's still a kind of twisted spin texture. And just to reiterate the point, this skyrmion, of course, is essentially a quantum of this emergent magnetic field. So if you integrate this emergent magnetic field over a magnetic unit cell of this skyrmion, you would end up with an integer number, namely the skyrmion number. And Caitlin mentioned this quickly, but I wanted to show you a nice picture related to it. So recently, I promised to talk a little bit about myself. So I started a new group at University of Tokyo maybe 1 year ago now. So we have a number of master and bachelor students. But if you're interested to join as a postdoc or a PhD, please contact me. And our techniques are mostly material synthesis, so this is an experimental group, of course, and we both make new materials and we study transport properties. And I'm not so familiar yet with spintronics, so this is one reason for me to attend this very nice conference. But so far we are mostly interested in thermoelectric response, such as Nernst effect, and then the thermal Hall effect, what Caitlin introduced earlier. Okay, so let me talk about kind of spin chirality in a skyrmion lattice, namely a thermoelectric response. So here, maybe for people who are not familiar at all with thermoelectric responses, essentially you can convert a temperature gradient to a voltage. So it's useful in the engineering perspective because you can recycle energy which is lost in all kinds of, kind of mechanical processes where you, for example, heat a motor and you would want to convert that energy back into electricity. That would be typically like a grant proposal type of explanation of what we want to do. So in the skyrmion lattice, we kind of wanted to study the Nernst response of the skyrmion lattice. So in the thermoelectric responses, there are essentially two types. If you apply a temperature gradient along a plate-like sample, you would have a voltage which drops parallel to the temperature gradient and also voltage which is perpendicular to a temperature gradient. And this perpendicular voltage typically needs time reversal symmetry breaking, so it typically needs a magnetization or magnetic field out of the plane. So we study this effect in this very kind of primitive setup where you just have a crystal, this black plate. You attach some wires, you attach some thermometers, which are somewhat out of focus in this picture. And you can then measure temperature gradient and voltage on your sample. And you can calculate the ratio of the two to get the efficiency of conversion between temperature gradients and voltages. And the challenge, of course, is to measure, if you want to have a precision measurement, you would have to measure relatively small temperature gradients and relatively small voltages. But of course, the signal can be extremely large. And the point here is that in the skyrmion lattice, the Nernst signal actually turned out to be extremely large in this gadolinium-2 palladium-silicon-3 compound. This was published about 2 years ago. So here we compare the signal to these kind of very well-studied ferromagnetic Weil systems that, for example, Claudia Felser has worked on a lot. So for example, cobalt-2 mangan gallium has a very large Nernst response that was kind of advertised as a technologically relevant property of this new type of ferromagnet. And in our skyrmion lattice system here, you would see that it's not on the same size, but on the same order as this very large ferromagnetic signal. So you would have essentially a different paradigm to create a large thermoelectric response from a twisted spin texture. And here what we're using is to quantify the response as this object alpha xy over t. So this is what's called the thermoelectric conductivity. I just want to make this point because this is not directly the Nernst effect that we measure, but essentially something related to the Fermi energy property of the band structure. Okay, so where does the signal come from? Maybe the simplest explanation or the simplest scenario of this kind of transverse response would be, again, a skyrmion. And this is a very famous kind of description that is very common in this field. So when you just consider an electron moving through a twisted spin texture, you could set up a Hamiltonian like this, which just includes kinetic energy and some sort of coupling between a conduction electron spin sigma and the local moment m. And then in order to simplify this term into a kind of two separated equations, you would apply a unitary transformation, which is just a local rotation of the coordinate frame at each atomic site, essentially. And then you would have this simplified Hamiltonian, which includes an emergent vector potential. And this emergent vector potential then translates into this magnetic field. So you would basically create an effective magnetic field through this unitary transformation acting on the conduction electron. And just to contrast the issue with the anomalous Hall effect that is popular in the field of kind of momentum space type Berry phase physics, we are focusing essentially on this emergent magnetic field in the real space scenario. But the equations are very similar. And if we go to the semi-classical Boltzmann description, we have to consider the kind of these semi-classical equations. And in both cases, we have a correction term, but the correction term appears in a different equation. For example, in the momentum space picture, you would have this anomalous velocity, which is closely related to the anomalous Hall effect, for example, in Libor's talk. But in the real space scenario, you would have an emergent magnetic field that acts just like a spatially homogeneous magnetic field in real space. But of course, this separation that also Caitlin talked about is somewhat artificial. There should be some sort of universal theory, and people consider these two separate limits. And of course, one of our research interests would be kind of to see, what happens when we push these two things together. And for example, in Germany, I think the Jülich group has done quite a lot of work trying to merge the two, for example, creating a 6-dimensional Berry curvature and so on. But I think this is still an open question, like what is the crossover between these two limits? Okay, I want to move on to a very closely related issue, namely kind of this real space picture of spin chirality, but as generated from chirality fluctuations. And I think Caitlin has given a very nice introduction, so I'm going to skip one slide here. This is just a repeat. And I'm going to go directly to another picture that Caitlin showed nicely, Jirong Zhang's paper on the topological charge in a kind of Heisenberg square lattice magnet with DMI. So in our work, we are interested in this kind of local spin cluster scenario that was pioneered by these theoretical simulations. But in our work, we do not look at a square lattice, but actually we look at these kind of Kagome type spin structures. This kind of distorted Kagome lattice that I will talk about in the following has the advantage. So if we have some sort of spin clusters in the material, we can essentially have a relatively simple theoretical description. For example, you can, in the Monte Carlo level, sometimes just calculate the spin chirality on a single cluster, and then just assume that your whole lattice is made up of individual clusters that are non-interacting. Of course, it's a crude approximation, but for the beginning of this kind of research, we thought that it was quite interesting. So I will first talk about a recent unpublished work, namely kind of motivated by Caitlin's research. So Caitlin talked to you about this square lattice system and as a simple Hamiltonian to kind of describe a thermal Hall effect on this system. And of course, I think this is interesting in the field of kind of fundamental discoveries related to thermal Hall effects, because it is a new transport signature or new thermal Hall effect that is not observed in a long-range ordered state. So as you know, there's a lot of work in the last 5 or 6 years on spin liquids, which can create a thermal Hall effect due to boundary currents or due to bulk properties. For example, this is a very famous work on a U1 gauge field in a kind of spin-on Fermi surface system. Then, of course, this is a kind of a mega hit paper where they discovered, or they claim to have discovered, a boundary heat current. And then, of course, there's also what's called the phonon Hall effect, where phonons themselves can acquire chirality due to coupling to magnetic moments. So all of these thermal Hall effects are essentially related to heat flow in a non-long-range ordered scenario. And we believe that this scenario that Caitlin has talked about in the previous talk is kind of a new representative of this family of thermal Hall effects. So we are focused on a spin cluster material here, in this case a pyrochlore system, ytterbium titanate. This is a very famous material in the field of frustrated magnetism. We studied the thermal Hall effect in this very primitive setup. So you just have a sample, you put a heater on it, some thermometers, you just put it on some sort of plate-like setup, you cover it with a radiation shield, and you just measure temperature differences in response to your applied heating power. And this material is a ferromagnet at low temperatures, but above TC we observe a very large thermal Hall effect response, so a sideways deflection of the heat current. And the one advantage I want to emphasize here is that very large and beautiful single crystals are available for experimental studies, and the system has been studied very thoroughly using neutron scattering, for example. So this is the experimental result. You can see here a heat map of the thermal Hall effect, or kappa xy, the thermal Hall conductivity, as a function of temperature and magnetic field for this pyrochlore system with the kind of tetrahedral spin clusters. And here what we observed is essentially that the thermal Hall effect becomes extremely large above TC, but this black curve here would be the ferromagnetic state, and the signal drops rapidly when we go below the long-range order transition. And here I'm plotting a variety of cuts through this data at different temperatures as a function of magnetic field. So we are currently in the process of trying to model this system using a theory very similar to Caitlin's, but we're struggling with this boundary current that she described. So somehow the combination of this bulk response, the Kubo type response, and this boundary heat flow for this more complicated crystal structure, which is not two-dimensional, unlike Caitlin's system, it's a bit tricky. Okay, before concluding, I want to show you some analogous physics in metallic systems. So how much time do I still have? Okay. 4 or 5 minutes, great. Okay, good. So this was unpublished work I should show you with the thermal Hall effect, but we have quite a bit of recent results on metallic systems where you can essentially probe the spin chirality just with the conduction electrons. In that sense, these systems are kind of more convenient, as I will describe to you in the following. So we are focused on this Kagome structure, which in one of the first slides I showed you has a skyrmion lattice at low temperatures. But now we're interested at relatively high temperatures in the fluctuation regime. So we kind of destroy the long-range order by thermal fluctuations, but we still observe a very large kind of Hall response of conduction electrons. So the nice thing about metallic system is that the spin fluctuations, of course, they're on the kind of megahertz or gigahertz frequency scale. but the conduction electrons typically have a much higher or faster kind of response time. So you can kind of assume that at every instant, the magnetic texture is static, and the electron just feels kind of the homogeneous emergent magnetic field at that moment, and then you just do a time average. So the separation of timescales for the conducting systems is very convenient. Whereas if you go to the insulating systems that Caitlin talked about, you have to then start worrying, you know, like, can I really define some sort of coherent excitation anymore? What does the signal really mean, and so on. So here I think we can, even above TC, although the spins are fluctuating rapidly, essentially for the conduction electron, every spin texture looks static at a certain instant. So we're looking at this Kagome structure. It has essentially these trimers of spins, and this Kagome structure is not the perfect Kagome, but somehow distorted, so you have like these larger triangles and smaller triangles. So we are kind of approximating the system in our recent paper just as a simple set of disconnected triangles, which each of them can create this spin chirality at a certain point in time. But due to finite DMI on the microscopic level, you can have an average spin chirality even above TC. So the main experimental signature that we uncovered here is a kind of comparison between this Kagome structure and a triangular lattice material. So in the Kagome structure shown here, you would have this very large spin chirality above TC, which kind of qualitatively at least looks very similar to the simulation that Jiadong did for the square lattice. So you would have a large spin chirality above TC, which persists to above maybe 4 or 5 times TC. This energy scale here, where the signal starts to decrease around 70 Kelvin, is actually the nearest neighbor kind of exchange interaction, so the kind of Curie-Weiss temperature around 70 K, but the long-range order appears at much lower temperatures. But in the triangular lattice, due to cancellation from nearest neighbor triangles, there's a very famous theorem that the spin chirality on a triangular lattice should essentially cancel. The signal is absent. So the contrast between these two materials, between the triangular lattice and the Kagome lattice, to us indicates that the kind of microscopic geometry of the lattice is crucial to amplify or suppress this kind of spin chirality effect in the dynamic regime. Okay, so I guess I'm... One more minute, okay. So I think I'm just gonna move ahead and skip the emergent inductance. Sorry, okay. I'm gonna conclude here. Maybe there can be more questions. And if there's no questions, I will talk to you a little bit about the emergent inductance. So I want to acknowledge my collaborators and of course my former boss, Professor Tokura, and especially also Kamil, who did a variety of experiments on the fluctuation issue, and Jan, who is a former member of Professor Roche's group and was in Japan for several years and has supported us a lot with theoretical calculations. Thank you very much.